This is BTC Tutoring Center, and we're going to discuss Chapter 4, Discrete Probabilities. So our introduction is a discrete random variable describes the outcome of a statistical experiment or survey and contains only a set of countable numbers for possible outcomes. For example, the random variable x of the number of heads in 3 tosses of a coin can only occur as the following: x equals 0, 1, 2, and 3. So x has 0 heads, 1 head in 3 tosses, 2 heads in 3 tosses, or 3 heads in 3 tosses. So the learning objective in this chapter, the students should be able to do the following: associate discrete random variables to a probability distribution function, calculate probabilities for the random variable based on the frequencies of the outcome in the experiment, that is, apply the rules for probability when necessary, compute and describe the mean, expected value, and standard deviation of a probability distribution for x, recognize the binomial probability distribution and apply it to specific problems, and recognize a geometric probability distribution and apply it to specific problems. So now we're going to look at an example of a discrete probability distribution. In a traffic survey of a number of car accidents occurring on Mondays for the month of June 2018, in 10 randomly selected 50,000 or less population metro cities in the United States, the following probability distribution shows the random variable x equaling the number of car accidents occurring on June Mondays. Right, so x is a discrete random variable, and here's our table: x equals 0 to 6. The frequencies are the following: 3, 5, 10, 12, 6, 3, and 1. And then we have p of x, which is the probability of each one of those frequencies occurring for the variable x. It's important to note for the random variable the different rules that have to be applied. For example, the rule of p of x has to be between 0 and 1. It could equal 0 and it could equal 1. And the sum of all the probabilities for the table, right, have to add up to 1. Remember, the mean value of the probability distribution is the sum of x times p of x, and the standard deviation is going to be the square root of x minus mu squared times p of x. And for this problem, when we do it, we get mu is equal to 2.65 and sigma is equal to 1.406. And in this case, we could use the TI-83, and we can go to the stats key, and we could look at letting L1 in our spreadsheet be the x value, 0 to 6. And we can also look at the frequencies to be L2 from 3 to 1. And then when we hit the calculate under stats, we can go over to one variable stats and hit L1 as the X list and L2 as the Y list and calculate. And this is what we get for those numbers. We're now going to look at the binomial distribution. X is approximately binomial with n trials and p of success. The binomial distribution is used when each trial in the experiment is independent from each other under a fixed number of trials. There are only two possible outcomes, success or failure, and the probability of success, P, and the probability of failure remains the same for each trial in the experiment. So under the binomial distribution, n is equal to the number of trials. P is the probability of success of each trial. X is the number of successes in n trials. The mean in this distribution is n times p. And the standard deviation is sigma is equal to the square root of npq. Note q is equal to 1 minus p. So we have an example here. Suppose 70% of the statistics students do their homework in time for it to be collected and graded. In a statistics class of 50 students, what is the probability that at least 40 students will do their homework on time? So in other words, we're trying to find the probability that x is greater than or equal to 40, right? This is a binomial situation because each student theoretically independently does their work from each other students to turn in their homework on time. We're going to use this calculation 1 minus x less than or equal to 40, that is the complement, because the way the calculator calculates is going to be this calculation. So in this particular case, we know what the P of success is. It's going to be 0.70. N in this case is going to be 50. And x in this case is going to be 40, right? So now we're going to use our calculator. And as you can see, we're going to hit the second key and then the vars key. And when we do that, we get this menu screen, and we're going to come down until we get the binomial CDF, right? And so now we hit that key, we hit enter. We're going to get the number of trials, which is 50. P is 0.7, x is 40, and we're going to paste that in. And we get a value of 0.957, but we're going to take 1 minus this value, so we hit the second and answer key, which is down there at the bottom, and we get 0.04. So it's about 4% of the students in this particular case that at least 40 or more of the students do their homework on time. It's about 4% of the time that occurs. So we're going to also look in this chapter on the geometric distribution. Here x is approximately geometric with a probability of success. And here the geometric distribution is used to find the first case of a success in x independent trials. Here the probability of success for each trial is the same. X is the number of independent trials until the first success. P is the probability of success of each trial. And mu in this case is 1 over p, that's the mean value. And sigma is going to be the square root of 1 divided by p. So we have an example here. Assume the probability of a defective computer component is 0.02. Find the probability that the first defect is caused by the 7th component tested. Well, here we want to find x is equal to 7 under the geometric, right? So p in this case is equal to 0.02. X is equal to 7. Okay, so we'll let our calculator do the work for us. So again, we're going to hit the second key and the vars key. We get this menu screen of all the distributions, and we're going to go down to the geometric distribution. And it's the geometric PDF, so that's what we're going to hit. We're going to let p is equal to 0.02. The value of x is going to be 7. And we've had some trouble with our fingers here. It should be 7. There it is. Now we hit the paste, and we hit it again, and we see that the probability of finding the 7th component tested to be defective is 0.0177. About 1.8% of the time we will find the 7th defect, or the 7th component, to be defective. Well, that concludes our discussion on Chapter 4. We have a worksheet available for you that you can go through as well and make your notes.